Hello there, welcome back. We actually begin with mutation testing in the second lecture of this week. I'll introduce you to what the concept is, first through an example, and then we will look at the general theory of mutation, look at some definitions related to mutation testing. So let me skip through a few slides because I wanted to start with an example. Yeah, so let's say I want to apply mutation testing to the following method. So the method that you see in the screen is a simple one, toy example. It takes two numbers, integers a and b, and computes the minimum of a and b. So the way it does it is it says initialize minval to a first locally, and then check if b is less than a. If b is less than a, then the minimum of a and b better be b. So reset minval to b, return minval. So between a and b, whichever is the minimum, this method will return it. So this method per se is right, but as an example, let's say I want to apply mutation testing to this method. So this is the program that I take, and I want to mutate or make one change somewhere in this program and test it and see. So the program that I have considered now in the jargon of mutation testing is called the ground string. And I'm going to make one change to this program called the ground string. And the change that I'm going to make is given on the right hand side. This is a copy of the same program that we had on the left hand side, but there is one extra line here, delta 1. So it's the same copy. And delta 1, read it as instead of minval equal to a, consider the changed statement. That is, consider the statement minval equal to b. So this is the method that we had considered here. I'm replicating this method, and I told you I'm going to make one change to the method, right? So the one change that I'm going to make is in this statement minval equal to a, I'm replacing minval with b. So that I represent as delta 1. So on the left hand side is the original program called the ground string. On the right hand side is the program with one change in it. And the one change is minval equal to a is replaced with minval equal to b. A is replaced with b. So this program on the right hand side doesn't have the statement minval equal to a. Instead, it has delta 1, which is minval equal to b. Even though it is given here, it is not there. Instead of this statement, minval equal to b is there. This is how you read the program. This resulting program with this one change of a being replaced with b is called a mutant. So the original program is the ground string. The resulting program with one change made is called the mutant. Now, I want to write a test case and execute the original program on the test case and the mutant on the same test case. And I want to get different outputs by both these programs. So let's assign something. Let's say A is 5, B is 8. Run the original program on A equal to 5 and B equal to 8. That is this program on the left. It will correctly return minval as A, 5. Run this program with a equal to 5 and b equal to 8, what will it return? Think for a minute. So here it will say minval equal to a, so it will assign 5. The statement is not there. So here it will say minval equal to b. It will assign 8. It says if b is less than a, set where minval is also equal to b. So b is not less than a, so it will not set minval equal to b, but because it had assigned minval to be b, it will return 8. So it won't return the minimum. So the output produced by the original program on the test case a is equal to 5, b is equal to 8 is different from the output produced by the mutant on the same test case. So in this case, we say that the test case has killed the mutant. Of course, this program didn't have any error. So mutation testing didn't show the error. But this is how mutation testing is typically applied. You take a program, it's called the ground string, apply one change to the program somewhere in the code. The resulting program is called a mutant. Write a test case where the output of the original program is different from the output of the mutant. And in this case, we say the test case has killed the mutant. This is the most fundamental idea in mutation testing. Even though this example didn't illustrate it, typically we apply that one change to the statement where we suspect the programmer could have made a mistake. Like for example, in this program, let's say the programmer made a mistake and instead of B is less than A, the programmer wrote something else. I suspect that there is an error in that statement. So we mutate that particular statement and then write a test case that will distinguish the output of the original program from the output of the mutant to illustrate the possible error that the programmer could have made. So that's the use. This example doesn't illustrate the use, but it illustrates the process of mutation testing. So with this background understanding, let me go back by a few slides and explain to you what mutation testing is about. So mutation testing involves making syntactically valid change. By a syntactically valid change means, suppose I take a program and change the source code of the program, the resulting program should be syntactically correct. It should be compilable. So mutation testing involves making a syntactically valid change to a program or in general other software artifact and then test that program. So this valid change is made in the underlying grammar of the software artifact. Programs that we write, C, Java, C++ programs, all have an underlying grammar, as I told you in the last lecture. Program is viewed as a large string in the grammar. So when I make a change to a program, what I am doing is I'm making change to one derivation rule in the underlying grammar of the program. And the resulting program should be syntactically valid, should be compilable, and I test the program with respect to its mutant. Sometimes I also mutate inputs to code. Sometimes I mutate design elements. So whenever I mutate code or design artifacts, the resulting mutant should be syntactically valid. Whenever we mutate inputs, the resulting mutant can be both syntactically valid or can be invalid to represent invalid inputs. You might want to test how the program responds to an invalid input. So some terminologies in mutation testing. Ground string is the string in the grammar, that is the base software artifact or the program to which we apply mutation. It's called the ground string. It's a string generated by the underlying grammar. Mutation operator is basically one rule that specifies one syntactic variant that you specify on the program. Mutant is the result of application of mutation operator. Exactly one application of mutation operator, as we saw in that example. Ground string, as we told you, as we saw in the example, could be a program, which is again specified using an input, a grammar, could be an input string, which is an input to a program, and several different things. Appropriately designed mutation operators can be applied for all programming languages and tested. So here is an example of applying mutation to an input. You remember this grammar? We saw it last time. A stream is a sequence of actions. Actions begin with a G or a B, followed by an S and an N, S or a T and an N. S is a sequence of digits, minimum 1, maximum 3. T is also a sequence of digits, minimum 1, maximum 3. N has 2 digits followed by a dot, followed by 2 digits, followed by a dot, followed by 2 more digits. Digit can be any number from 0 to 9. Some strings generated by this grammar look like this. G, 17, followed by some date. B, 13, followed by some date, and so on. Suppose I have to mutate this. I make a change to one production rule here. And I can get valid mutants. Like for example, I can interchange B and G. So I can replace B with G and G with B and vice versa. I can replace some other number with some other number. All those would be valid mutants. Invalid mutants might just drop B or drop G, generate strings that are not valid as per this grammar. It might replace one of the 2 digits in the sequence that is meant to represent a date. As inputs, you can generate both strings that are valid and strings that are invalid and test how the program behaves on these inputs. So this is an example of mutating inputs. We just saw an example of mutating programs. Mutation operators are available for several different programming languages. I'll show you some of the mutation operators and the tools for specific programming languages. They are also available for formal modeling specification languages. They are available directly for grammars in Backus-Naur form. They are available for languages like XML, query languages like SQL, and so on. For programming languages, mutation operators can be applied at the unit level within a method, like we saw for that example, or it can be applied at interface level also, at the call interfaces, where it can be used for integration testing. So we'll see examples of both kind, and we will see mutation operators specific to programming language like Java, and a little later we'll also see mutation operators specific to language like XML. So some more definitions before we move on. Let's say I have a program which in general is a software artifact, and that program can be mutated in several different ways. Let M be the set of all different mutants that you get. So take a program, make one change, you get the first mutant. Take the same program, ground string, make another change, you get the second mutant. Take the same ground string, make a change somewhere else, you get the third mutant, and so on. So now collect all these mutants. Let's say for a particular example, there are 5 different mutants available. Let M be that set. Each such mutant will lead to a new test requirement, and the goal is to write a test case that distinguishes the output of the ground string from the output of the mutant. You run the same test case on the ground string, you run it on the mutant, they both produce different outputs. So this notion we had seen for the example, it just formally defines it. Given a mutant for a derivation and a test case T is set to kill the mutant if and only if the output of T on D, which is the ground string, is different from the output of T on M, which is the mutant. So that was it. Now mutation coverages, as I told you, for a particular ground string you might have 4, 5, 6 mutants or 10 mutants. So for each such mutant, your test requirement says try to kill the mutant. Write a test case where the output of the ground string is different from the output of the mutant. Coverage and mutation equates to killing the mutants. And suppose I had 6 mutants for a given program, and I was able to write test cases to kill 5 of those mutants, then the mutation score that I get is 5 out of 6. Lower mutation score doesn't mean that I have done bad testing. Higher mutation score doesn't mean that I have done very good testing. Mutation testing can be used for showing errors or to produce equivalent mutants. I'll tell you what an equivalent mutant is. So when a particular grammar is mutated to produce invalid strings, then the goal is to run the mutant to see if the behavior of the program on that input is correct or not. For mutation operator coverage, we say for every particular mutation operator, test requirement contains a mutated string that comes as a result of applying that mutation operator. Typically, for a normal programming language, there are hundreds of mutation operators. So mutation operator coverage is not an easy requirement, and typically you don't apply all the mutation operators together. Mutation production is for each mutation operator, the resulting production rule is covered. Both these are useful theoretically, but you apply mutation only for a select set of statements in the program, typically wherever you suspect there to be an error. As I told you, this mutation operator coverage and mutation production coverage is typically never exhaustively done. So they exist theoretically, but we don't consider them one at a time. We typically apply it based on where we suspect errors to be there. So we will define mutation operators, learn how to apply it. As we saw in the example, we'll extend it. Then we look at integration mutation operators. Then we look at mutation operators applied to inputs, specifically XML, and see how it is useful for testing certain kinds of web applications. So this slide gives you a summary of all the mutation operators that are available for testing various kinds of software artifacts. We are not going to look at all of them in the course. This is just for the sake of completeness. Mutation operators are directly available for grammars. Compilers use them. They are available for algebraic specification languages. They are available for input languages, ordinary inputs like dates to input files like XML. They are available for programming languages, for mutating programs in common programming languages, Java, C, C++, C#, and so on. They are available for mutating finite state machines. Several different mutation operators are available. We are going to see one for Java and one set for XML. So now let's move on and look at program-based mutation. This is what I've been telling you. Begin with the program under test. Let's call that as ground string. Now it could be a whole program or it could be a particular method in a program. We apply one or more suitable mutation operators to that program, one at a time. And the resulting program is what we call a mutant. Mutants must be syntactically correct, in the sense that the resulting program as a mutant must be a compilable program. Remember, mutant is just a variant of the program under test. Mutant is not a test case. We will write test cases to kill the mutant. We saw this example. In this example, I've taken this statement, min_val equal to a, changed this a to b and got a mutant. And I can write a test case to kill it. We saw this. Now, this is not the only mutant that you can get. For this particular program, you can apply several different mutation operations and get several different mutants. So the next slide, this slide illustrates that. On the left-hand side, you see the original program, the program that we started out with. Just computes the minimum of 2 numbers. Simple enough to understand. On the right-hand side, there are 6 different mutants of this program. They're all squeezed into one code. How do I read this as representing 6 different mutants? The way you read it is these delta 1, delta 2, delta 3, and so on up to delta 6. Those are the specific statements that are replaced. So delta 1 represents the first mutant, where the statement min_val equal to a is replaced with min_val equal to b. So make a copy of this program. Instead of the statement min_val equal to a, consider the statement min_val equal to b. That will give you the first mutant. That's represented by this delta 1. The second mutant is, take this statement if b less than a, replace this less than with greater than. That will give you the second mutant. That is, make a copy of the ground string on the left hand side. Take this decision statement b less than a, replace this less than operator with greater than operator. That's delta 2. That's the second mutant. Third mutant is, take a copy of the same ground string, replace in this decision statement the argument a with min_val. That is delta 3 here, the third mutant. The fourth mutant is, instead of this statement inside the if statement, min_val equal to b, write a special statement called bomb. So what does the word bomb statement mean? I mean, these terms are catchy, so don't worry about why these terms are like this, killing, bombing and stuff like that. They're just standard jargon in mutation testing. So the term statement bomb represents a special method which indicates that there is a runtime error that happens when you reach that statement. So you can write any code for this bomb method, which basically indicates that an exception has occurred and the program stops execution. So the fourth mutant takes this ground string on the left hand side, replaces min_val equal to b with this special statement called bomb. Fifth mutant just takes the same min_val equal to b, replaces b with a. That's this delta 5 here. Sixth mutant again makes the copy of the ground string, takes the statement min_val equal to b inside the if statement and replaces b with fail on 0 b. So fail on 0 b is another special method which indicates test for division by 0. I'll come to that in a minute. So is it clear what we've done? This is just an illustrative example to show you various ways in which you can mutate programs. On the left hand side here, you have the ground string or the original program. On the right hand side, I have written one concise representation for 6 different mutants. We just walked through what the 6 different mutants are. What are they? Take a program and replace the statement just before the delta statement with the delta statement. That gives rise to one mutant. And there are 6 such delta statements. Each of them will give rise to a different mutant. So 6 mutants are there. So the goal in mutation testing is the same. I now write test cases, execute the ground string on the test case, execute each of the 6 mutants on the test case such that the output of the ground string is different from the output of the mutant. In such a case, we say that the test case has killed the mutant. So this slide explains what the mutants are. We had 6 mutants, out of which mutant 1, 3 and 5, which is delta 1, delta 3 and delta 5, basically replace one variable with the other. Mutant 1 replaces A with B, mutant 3 replaces A with min-val in the decision statement, mutant 5 replaces min-val equal to B with min-val equal to A. So mutants 1, 3 and 5 replace one variable reference with the other. Mutant 2, which is delta 2 here, changes this relational operator inside the if statement. So it replaces B less than A with B greater than A. That's mutant 2. Mutant 4 is what I explained to you. This bomb statement or bomb method. It's a special mutation operator that many tools will provide. They may not all call it with the same name, but there'll be some catchy indicative name like that. It basically causes a runtime failure soon after that statement is reached. Mutant 6 is another special mutation operator, fail on 0, basically causes a failure if the parameter that's passed to it is 0 and does nothing if the parameter is non-zero. It could return just the value of the parameter. Here, if you see delta 6 uses the fail on 0 mutant. If B happens to be 0, then delta 6 will cause a failure. If B is non-zero, then delta 6 does nothing. It is useful for checking if there is a division by 0 error in the underlying program, which is a very common error to have in a program. So if you see, for a small program like this, we were able to apply 6 different mutation operators. So imagine for larger programs, the variety of mutation operators that are available. Hopefully this example would have given you a good flavor of what you can do. To get mutants of a given program, you can replace one variable reference with another, one kind of relational operator that is present in the ground string with other kinds of relational operators. To check for division by 0 errors, you could write special mutants like these fail on 0. To just check for reachability of a particular statement, you could write special mutants like these bomb statements. You could change arithmetic operators and so on. Several different mutation operators are available for typical programming languages. What is the goal? As I told you, typically we don't apply all possible mutation operators and check for what is happening in each case. Somewhere in the code, you suspect that there is some kind of error, and you want to make sure whether that error is there or not. Errors could be low-level errors, like the programmer had to write less than, but instead wrote less than or equal to. So you want to check. So you take the original program which had, let's say, A less than B as a part of a decision statement. You make a mutant by replacing the less than with the less than or equal to and get A less than or equal to B. Now write a test case, execute both. If the test case succeeds in killing the mutant, your conclusion could lead to showing to your stakeholder that A less than B was not the correct choice. It was A less than or equal to B. So typically, mutation operators are useful for mimicking programmer mistakes. Maybe the programmer thought array indexing began at 0, but actually array indexing for the programming language begins at 1. Maybe the programmer intended to put ++i, but instead put i++. So no small mistakes where programmers can make because of non-familiarity with the programming language or for various other reasons can be caught by making an appropriate change to the statement where the mistake is suspected to be, resulting in a mutant, and writing a test case to illustrate this. So typically mutation operators, several different of them are available, but you pick and choose based on what is your need. Don't apply blindly without defining what your need is. Again, some more terms related to mutation testing. Please don't worry about the quality of the term. They are catchy, they may not be very pleasant, but this is standard terminologies in mutation testing. So we have a ground string. I apply one mutation operator to the program and I get a mutant. The resulting mutant is called a stillborn mutant if it results in programs that are not syntactically valid. That is, they cannot even be compiled. So we typically don't generate such mutants. A mutant is called a trivial mutant if it can be killed by almost any test case. Like for example, we saw here, this minimum, the first mutant that we saw for this min. Any decent test case will distinguish this ground string from the mutant. So this is an example of what we call a trivial mutant. An equivalent mutant is you make a change, but the resulting program actually has the same functionality as the ground string. So no matter what test case you write, you will never be able to get an output of the ground string that is different from the output of the program. So such mutants are called equivalent mutants. In our example, if you see these 6 mutation operators that we had, the third mutation operator is an equivalent mutant. Do you understand why? Because if you see, what does the third mutation operator do? If it takes this statement b less than a, if b less than a, and replaces a with minval. But that's not a very useful replacement, mainly because just in the previous statement in the ground string, minval was assigned a. So by replacing b less than a with b less than minval, you're not changing anything in terms of the behavior of the program. So the third mutant is an example of an equivalent mutant. So mutants that are functionally equivalent to a given program and no test case can distinguish or kill the mutant from the behavior of the ground string. Dead mutants are what we want. Mutants that are syntactically valid and can be killed by writing test cases. That is, mutants for which I can write test cases such that the output of the ground string is different from the output of the mutant on the same test case. Dead mutants are what we want for being useful for testing. Sometimes showing that a mutant is equivalent is also useful for testing. So now let's come back and look at the notion of killing a mutant. When do we say that a mutant is killed? If I am able to take a test case, execute the ground string on that test case, execute the mutant on the same test case, but the output produced by the ground string on that test case is different from the output produced by the mutant on the test case. Sometimes we may not want to have such a strong requirement in terms of insisting that the output be different. See, for the examples that we see in the lectures, we see small pieces of programs that have 10 lines, 20 lines. In general, mutation testing is applied to programs at the method level, maybe where there are a few hundred lines of code. So insisting that the output be different is a strong requirement. Instead, what do you want for a mutant to be killed? At the statement where I apply the mutation operator, if the state of the program, ground string, is different from the state of the mutant, for the statement or the variable that I suspect is supposed to have an error, then that is enough. So killing the mutant can be refined as strongly killing and weakly killing. Typically, when I suspect a particular statement to have some other value or some other error, let's say I say less than versus less than or equal to, then all that I want to do is I might write an assert or a printf there to check whether this is right or wrong. Instead, what I want to know now is, at that statement, suppose I change less than to less than or equal to, does my program behave correctly? It may or may not reflect in the output. So just reaching that statement and observing the change in that statement in terms of infection is enough. I may not want the change to propagate and produce a different output. So we refine the notion of killing to reflect this subtle change. So we say a mutant strongly killed if I am able to write a test case that distinguishes the output of the ground string from the output of the mutant. Is this clear? So it's the same notion that we saw killing earlier. Now we are calling it a strongly killing. That is, you take a program, ground string, make one change by applying a mutation operator, get a mutant, write a test case, execute the ground string on the test case, execute the mutant on the test case. If the output produced is different, then you say the mutant is strongly killed. Strong mutation coverage says write a test requirement to strongly kill every single mutant that you produce. The other notion is slightly relaxed. It says weakly killing a mutant. You take a program, apply one mutation operator, get a mutant, write a test case, look at the state of the program immediately after the statement, the place where you applied the mutant. If the state in the ground string is different from the state in the mutant in terms of the values of the variables being different, then you say the test cases weakly kill the mutant. Many times weak killing is enough for us. Sometimes we might want strong killing. Weak mutation coverage says for each possible mutant that you can produce, test requirement says write a test case to weakly kill that mutant. Yeah, so this just works out what happens in the minimum method. So let me just go back to this min method example that we had. So this is the one, and the first mutant just replaced A with B. So this works out reachability conditions for that method. Reachability is always true because that's a small code and I reach that statement. The statement of the mutant gets infected if A and B have different values. It gets propagated if the mutated version of min returns an incorrect value. So the full test specification is reachability is true, infection is A not equal to B, propagation is B less than A equal to false. If I simplify this predicate, I will get B greater than A. So any test case where actual values of A and B such that A is less than B will kill the first mutant. This is what we saw right in the beginning of this lecture. So suppose I take the third mutant. This again I explained to you. This is an equivalent mutant. Why? Because just in the statement before the mutation, I had assigned min val to A. So how do I conclude that it is equivalent? Again, work out reachability conditions, infection conditions. You will get a contradiction. Reachability is true. Infection is B is less than A, not equal to B is less than min val. But that's not possible because min val was equal to A by the assignment that happened just before the statement. So we get A not equal to min val and A equal to min val. This is a contradiction. So the mutant, we conclude that the mutant is an equivalent mutant. Here is another example. This example illustrates the difference between strong killing and weak killing. So this is an example that checks for divisibility by 2. So the method is called isEven. It takes an integer x. If x happens to be negative, the thing just makes it positive, statement number 4, and then it does division by 2. If it is able to successfully divide by 2, it returns true to check whether the number is even or not, otherwise it returns false. The same code also has the mutant. I hope you're comfortable with reading that. So the ground string is statements 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the original program or the ground string. The mutant is statements 1, 2, 3. Instead of 4, consider delta 4 to get the mutant. Then 5, 6, 7, 8 and 9. So this one code has the original program and the mutant. The original program has 4 statement, which is x is equal to 0 minus x. The mutant, instead of 4, x is equal to 0 minus x, has x is equal to 0. So what does the original program do? It checks whether a number is even or not. What does the mutant, what does line number 4 do? Line number 4 replaces every negative number with its positive number. If x I give it as minus 3, then line number 4 will set it to 3. What does the mutant delta 0 do? If it gets a negative number, it will make it 0. That's the change. Now, mutant in line 4 is an example of weak killing. Why is that so? Reachability is x less than 0. Infection is x not equal to 0 for this x. That's fairly clear. Now, suppose I give a test case -6. Then in the original program, if it's a negative number, line number 4 will make it 6. The mutant will make it 0. So 6 and 0 are both even numbers. So this line 5 will return true for both. Output will not be distinguished. But suppose I have to distinguish at the output, even though the state at the place of mutant 4 is different, because x becomes 6 in one case, x becomes 0 in one case, output stays the same. So this is an example of weak killing. Suppose I want the output to be different, then suppose I give it as -3. Then the statement 4 will make it 3. Statement delta 4 will make it 0. 0 is divisible by 2. 3 is not divisible by 2. So one will return true, the other one will return false. So for strong killing the mutant, we need the test case or the value of x to be an odd negative integer. Even negative integer will end up satisfying divisibility by 2 and the output will not reflect the change, but it will still be weakly killed. For strong killing, you need an odd negative integer where the output will be different. So this slide explains the process of mutation testing. It's a long process. This is how tools do it. So we take a program P, then we create mutants for the program P by looking at the list of mutation operators. I'll show you in the next lecture what mutation operators are. Then this third one is not an easy thing to do. It's typically a tough problem. You run to check whether the mutant is equivalent to the original program or not. For the purposes of our classroom teaching, we might create small programs so it's easy to run. In general, for larger programs, it's not easy to run. The equivalence checking. Then if it's not equivalent, then you generate test cases, run the test cases on the ground string P, run the test cases on the mutant, and if a test case is not effective, remove it, check whether a test case has been able to kill or not, that based on your threshold. Somebody gives you a threshold. Define 5 mutants, write test cases to kill all 5 mutants, define 10 mutants, write test cases to kill at least 80% of them. Things like that people will give as a threshold. So you check whether your threshold is reached or not. If your threshold is not reached, repeat the process of writing test cases, running it on the ground string, running it on the mutant and checking. If the threshold is reached, then you collect your results together to analyze if the original program had a mistake or not and conclude by fixing the program. So this is the high level process of how mutation testing is applied end to end. Yeah, so the basic questions are, I suspect, you might have this question of, I suspect there being an error in more than one statement in the program. So can I mutate all the statements where I suspect to be erroneous simultaneously? The answer is no. You typically apply one mutation operator at a time, not more than one. The next thing is for a particular program like that MinVal program, we saw 6 different mutants. Are all of them useful? Should I apply all possible ways of mutating a program and checking for it? Again, the answer typically is a no. You apply mutation only when you consider it to be useful to identifying a place, an error in a statement where you suspect that there is an error. Yeah, so it's a very powerful form of testing, and we will look at mutation operators for source code in the next lecture. I'll stop here for now. Thank you.